Hello, welcome back to your Theory 2. Okay, so we will now proceed on your Module 4. So this is now the analysis of steel, statically indeterminate structures, but this time using your what we call as the moment distribution method. Okay, moment distribution method. In your Module 2, we discuss your consistent deformation. In your Module 3, we discuss your slope deflection. And now this is your Module 4, moment distribution method. Okay, so what is moment distribution method? This was developed by Hardy-Cross in 1924 for the analysis of indeterminate beams in frames. So actually this is coming from this is just like a what to call this one. This is another concept which is related to your slope deflection. Okay. So again, your slope deflection comes first before Hardy-Cross developed your what we call as your moment distribution method. Okay, so this is almost the same as your slope deflection method, only that the end moments are determined by iteration, not by solving simultaneous equations. So if you will recall your slope deflection method, we are trying to create your equations in terms of rotations and unknown deflections, which are your what we call this one, the degrees of freedom. We call that one degrees of freedom in your slope deflection method. So we will be using those to calculate the end moments. Okay, and then that's it. Once you have your end moments, we will now be getting the reactions, and then of course you can draw your shear and moment diagram of any member of a frame or beams. So again, this is almost the same again as a slope deflection. And of course, they are the same, that this will just only deal with beams and frames. So there is no moment distribution on trusses. Why? We are talking here, if we say moment, we are talking here of the moment on members. So there is no moment on members of trusses, only axial forces. So therefore, this is just like again slope deflection only for beams and frames. So this is your what do you call this one? This is discussed in the following or the basic. This discussed in the following or the basic concepts of your MDM. We need to understand what are these concepts of MDM, so that you will now know how to use this one, or you understand how it is done. Okay. So for example, consider this frame here. So the moment at a joint is countered by end moments of all the members connected to that joint. Okay, so for example, look at this. You have there joint A. The moment, let's say you have there a moment at joint A. That moment at joint A, since of course joint A will not carry that one, since there is no fixed support at joint A, therefore the moments will be carried by the connected members to that joint, which are your member AB, member AC, and member AD. So that's why we call this one moment distribution, because we are trying to focus on a joint, and whatever moment, summation of moments that are there on the joints, of course, if that is a fixed support, then of course that moment will be carried by the support. But let's say that is just a joint, and there is an excess moment. Of course, that will not be stable. So that should be carried by the member connected to that joints. Okay, since again we are trying to consider the equilibrium of the structure. So that is the first concept, basic concept. That's why we call this one moment distribution. Okay. So if you will try to, let's say, cut just after your joint A. Okay, you have there your moment M. That is the moment at joint A. Then that will be distributed again. So if that is clockwise, that could be countered by this MAB, MAC, MAD, which are actually the end moments of your member AB, AC, and AD. Okay. So again, if you'll try to recall your slope deflection equation, these are your slope deflection equations, isn't it? So these are your end moments. So let's say I will consider member AB. Okay. Wherein that member AB is fixed at joint B. Okay, so MAB will be 2EI over L, okay, whatever the length of that AB, times the quantity 2 times the theta A, since we are referring here at joint A, plus theta b. Since again there is no rotation at joint B, since that is a fixed end, then that will be 0, and there is no, let's forget first about Sidesway. So let's say that is totally braced from lateral sway. Okay, so that will be 0. So your moment, the end moment at AB, that MAB here, will be 4 EI over L theta A. Okay, what if we will consider? Okay, consider your member AD, simply supported end. Okay, this one, AD. Okay, because by the way, why are we trying to consider the other end of the member? Okay, all we need to do is distribute that moment. However, of course, the connection on the other end of the member matters, because if that is free, for example here, look at this, your member AB, that is fixed. So of course, you will expect that the more moment will be handled by that AB compared to your AD. Why? Your AD is just pin connected at joint D. So once this will rotate, that will also rotate. So again, this is free to rotate at joint D. Therefore, that will only carry less. Okay, for that to be stable, that will only carry less moment compared to your AB and of course your AC, since they are both connected on the other end to be fixed. So again, why? Even if this will carry a little much bigger moment than your AD, because again that will be carried out or be supported by your fixed support on the end of these members. So again, for a fixed end, the moment that will be carried by that is 4 EI over L A or theta A, or that is simply the rotation at the joint that we are considering. If we will consider that simply supported still from your ST equation, 2 theta E over L. However, theta A is free to rotate, joint is free to rotate, and at the same time theta D, since that is not a fixed, so that is also free to rotate. So we have there theta D. So theta A, theta D, and again, let's forget first about your deflection. Okay, so simplifying this one, this will be our MAD. Okay, MAD. However, if you will try to get the MDA, okay, the MDA, there should be no MDA. Why? That is simply supported. It could be, if you say simply supported, that could be a ruler or a hinge. This type of support will not offer a moment reaction. So these are supports that are free to rotate. So if this is free to rotate at joint D, then there should be no moment of that. For that to be equilibrium, there should be no moment. There should be no end moment, DA. Okay? Then, unless of course there is a counteracting moment or a moment load at joint D for that to counteract that MDA, if ever. But let's say there is none, then that should be 0. That should be 0. So if that's the case, if I will equate that to 0, 2 EI over L, this will be cancelled. Since that is 0, you can cross multiply, that will be cancelled. You are left with 2 theta D plus 2A, cross multiply, transpose theta A on the other side divided by 2. You will have the value of theta D, substitute it back, and our MAD, then you will have that in terms of theta A. Then simplify that one, your MAD will become 3 EI over L theta A. So that is our MAD. That is what will be carried by AD, since that is simply supported at the other end. For a fixed support, it could be AC or AB, that will be carrying 4 EI over L theta A. So look at that. Let's consider that all of these have the same length. So the fixed support on the other end will carry 4. Let's say, since these are the same, EI over L times theta A are the same on all the members, let's just focus on the number 4. And the one carried by simply supported is 3. Therefore, you can say that the one that will be carried by a simply supported on the other end is just, okay, look at this, 3/4. 3/4 of the one to be carried by the fixed support. Okay, so if you will try to distribute, okay, you will try to distribute your moment at joint A if there is an excess. Okay, if you will summate and there is a moment, there is an existing moment at joint A that should be carried that should be distributed by the connected members, and the way of distributing this one is, okay, 4 EIL times theta on the fixed support, and then 3 EIL theta A on the simply supported other end. Or again, what will be carried, again, let's say that is a constant, they have the same length, they have the same I, they have the same I, E, then of course we are referring here to theta A, so that will also be the same. So the only difference of the fixed end and the simply supported end is that this will be carried 4, and that will be carrying 4, and this will only be carrying 3. Or simply, a simply supported will carry 75%. That is 3/4, or that is 75% of what will be carried by a fixed end. So fixed end members. Okay. So if that's the case, then okay, let's try to talk about what we call as the bending stiffness. These are actually the 4 EI over L. That determines the strength of the member. Okay, let's say that, of course, let's say that these are varying lengths and these are varying moment of inertia. The members have this different moment of inertia, and they have different what we call this one, lengths. But however, seldom that we will be ending up with different types of material. So most of the time we will expect that E is constant. Okay. So this actually determines, since theta A and theta A are just the rotation at A, then the strength of each member with respect, because of course you cannot say, if let's say the size of the member AC is different from the size of member AB, then the bigger the member, the bigger moment it will be carrying. So again, that is what happens if they have different size and different lengths. So we will try to put that as the bending stiffness. Okay, so the bigger the bending stiffness of that, the bigger the moment it will be carrying. Okay, so that stiffness is the moment that must be applied to have a unit rotation at the joint. Or simply you can say, let's just make theta as 1. Okay, theta at the joint as 1. Then what remains there, or what moment that will be required to make that 1 is actually your bending stiffness, or that is the strength, or that is 4 EI over L. So for a fixed end, our bending stiffness is 4 EI over L, and for our simply supported is 3 EI over L. 3 EI over L, this one. However, since again it is always simpler to express one quantity on another, since later on we will be solving it, so that you will not be confused. But it's okay, you can use this as is, as 4 EI over L, and then 3 EI over L. But again, for simplicity, we can express that simply supported in terms of your fixed end. So again, that is just 3/4 of the fixed end, so that you can say that if you have the stiffness of a fixed end, that is just a 75% or 3/4 of a simply supported end, if they are identical on I and L. And of course, again, as I've said, E could just be constant, since seldom that you will be having different types of material connected at a single joint. But for the case of, let's say, you have a column which is concrete and you have a beam which is steel, of course the E there is different. So that's the time you will end up with E which are different. Then again, for simplicity, let's say that E are constant, and then of course you can just now divide your fixed end and simply supported end by 4E, so that you will simplify. So we call this one relative stiffness. If they have the same E, if they have constant E, or that is the same type of material, then you can actually forget about 4E and then 4E there. So you are just left there with your relative stiffness, which is your K. This is your K bar. K as your 1 I over L. Okay, for fixed end, that is I over L. For simply supported, that is still 3/4 or 75% of I over L. Okay, where are we going to use this? Again, as I'm saying a while ago, that stiffness determines the strength of each member. So the stronger the member, the bigger the moment it will be carrying out from the total moment on the joint. Okay, so that is what we need to consider. The stiffer the member, the bigger it will be carrying. And if the other end of that is what we call this one is fixed, that will be carrying a bigger moment compared to another member which has a simply supported end. Or in relation to that, you can say that what will be carried by the simply supported is 75% of the fixed end member. Okay, that's it. So we will be using this. Therefore, we should know how to divide this one, isn't it? So that is the question here. Because again, what we are trying to after here is to distribute the existing moment at the joint for that to be equilibrium, since there is no support. Okay, so how will I do that is, again, I need to know what percentage will I give MAD, what percentage will I give MAC, and your MAB. Or simply say, what percentage will I distributing on each of the members. So this is now what we call as the distribution factor, or that is the percentage of the total moment to be given on each of the member. Okay, so a total moment at the joint is distributed in each member with respect to member stiffness, okay, or that is again with respect to their strengths. Okay, that is fixed support on the other end, that is stronger compared to a simply supported. And again, the bigger the area, okay, as you can see, look at this, the stiffness. Now let's focus here. The bigger the area, the bigger your I. The bigger the length, the smaller, of course, the total K. So your stiffness is proportional to your cross section or the area of that. Again, your I is coming from the area, isn't it? And then your L there is coming from the, of course, that is the length. So your stiffness is inversely proportional. The bigger the L, the smaller the K. So what does that mean? Let's say you have the same, okay, for example, let's go back here. Let's say this AB and AC have the same situation. They are fixed end supports. But let's say, okay, let's say even they have the same area. If your AB is longer than your AC, then the bigger or the stronger your AC is. Okay, let me give you an example. Where's that? Okay. For example, okay. For example, this. Okay. So let's say this is your member. If you are going to bend that one, okay. If you are going to bend, or let me find a solid. Let me find a solid material. Okay. So let's say this one. This is this stick. So the smaller that one, the smaller the length. If you try to bend that one, that will be harder compared to a longer length. Okay, that will be a little bit weaker in terms of bending. The longer, let's assume that is constant. Of course, comparing a small length with a long length, consider that they have the same size, cross-sectional area. So the longer that one, that is weaker compared to the shorter. So you need to shorter member, with the same side, the same cross-sectional area. So, okay, what I'm trying to say here is that, again, your total moment on the joint is distributed with respect to the strength of each of the member. So that will be equilibrium, because you cannot just transfer all the existing moment on the joint on one member and the other one is not working. Then that will make it unstable, isn't it? Okay, for example, this is the joint. You have an existing moment here. You will transfer it only there. Then that will fail. This will be useless. The other member will be useless. And if you try to transfer all the loads here, that will actually be unstable, because that will be just moving, or the entire structure will just be moving or deflecting. Okay? This is the concept of your what we call this one, moment distribution. The existing moment at a joint should be balanced or should be distributed in all the members connected to that. Okay, so as you can see, this is our original equation there again, for this case only. So distributing your total moment to AB, AC, and AD. However, let's try to simplify that for EI over L using your K bar. Okay, instead of writing there for EI over L, let's write there K bar for AB. And then K bar for AC, K bar for AD. It means they are different because, of course, later on they will be different with I and they will be different with L. Okay, so it means that if I will factor out every moment there is in terms of theta A, so you can factor out theta A, then you will summate this K. You can say that that is theta A times the summation of all the stiffness of the member connected. However, as what I'm saying, if your E is constant, then you can just worry. You can just worry about your I and L. So we will be using your relative stiffness if E is constant. Okay, unless again, okay, but you can still use E, no problem with that. But that will just be additional thing for us to be writing on the solution, or for us to be dealing with. So if E is constant or the material is the same all throughout, then you can just simplify it by using the relative stiffness. You can forget about E, just deal with the I and L, since most of the time, really what differs on the connection, for example, on the actual connection of a column and a beam, the cross-section of the column is different from the beam. So the I of this column is different, and at the same time, of course, their lengths are different. So that is relative. So if you want, you can use your moment is equal to, or let's say you can cross-multiply summation of K bar there, you will have theta A is equal to summation of K bar, M over summation of K bar. Okay, but again, you can say that is theta A is M over summation of K only. Okay, so if that's the case, then you can say considering member AB, what's that? Member AB again, fixed N. Then you can say that the since theta A there is M over summation of K, where's that? Yeah, I'm here pala. MAB is KAB theta A. So if that is your MAB, then you can change the theta A in terms of the summation of K, so that you will have here KAB times your, again, value of theta A, which is M over the total moment over summation of K, or you can just simplify that as the percentage or the amount of moment that will be given to AB is equal to the percentage of the K of its stiffness with respect to the total stiffness. That is the meaning of that. Or that is just the ratio or the fraction of its member stiffness with respect to the total stiffness of all the members on the joint. So that's it. If you want to distribute, then if you know the total moment on the joint, for you to get the moment to be taken by AB, that is stiffness of AB all over the summation of all the stiffness of the connected members. Therefore, that can be simplified here. This will serve as our distribution factor. Okay, so the K bar or the bending stiffness over the summation of bending stiffness of all the members. Multiply that one with the total, that is what will be carried by the member. Or again, if E is constant, then you can just say that that is the relative stiffness K all over summation of K. So that is how we will distribute, so that you will know how much will this member hold from the total moment. Okay, so one more thing here is that if, look at this, if that is, for example, only if this is a clockwise moment on the joint, then that will be carried, or that will be counteracted supposedly by an opposite direction, isn't it? Okay, so we call that one balancing, so that this will now be the joint A will be in equilibrium. The direction or the sign of the existing moment should be countered by the members. Okay, so you should know about that. However, now, if you transfer the moment into the members, what happened there? If you will try to put the moments on AB and AC and AD, what happens is that the other end of those will be affected. The other end of the members will be affected. We call that one, okay, so there will be an effect of that. If you will transfer that at A, joint A, or just after joint A, that will be affecting your joint B. And you will transfer that MAC at your member AC, there will be an effect at C, and there will be an effect at D. We call that one the carryover. Okay, so that is what we call the carryover moment. Okay, so what is carryover? That is the moment induced on the other end of the member due to the moment applied on the end being considered. Okay, so that is what I'm saying a while ago. Okay, so if you have here the moment, let's say again you are balancing the moment at joint A and you are going to balance that, and there is a moment that will be taken by your member AB. The moment which is taken by that member AB will induce, okay, will have an effect on the other end. That is what we call the carryover moment. Okay, so again, if you'll try to recall a while ago that MAB, since that is a fixed end, that is for EI over L, okay, theta A. Then if you will try to get your MBA, okay, so MBA is the end moment on the other end, isn't it? So what happened there? You will get that MBA, go to the slope deflection equation. So slope deflection equation was that this, okay, so what happened? MAB, theta A will be twice, but if you will get your MBA, your theta B will be the twice, and then theta A will be 1. But theta B is fixed, so that is 0. So again, this will be 0. Theta A is only 1 there, therefore that will be 2 EI over L times theta A. Theta B here will be 0, that delta will be 0. So that is how we have this MBA, which is 2 EI over L theta A. So again, if you try to compare MAB, okay, that is the joint that we are considering. Okay, the MAB is actually 4 EI over L, and the other end is your 2 EI over L. So as you can see, the induced moment, okay, the moment on the other end, okay, due to theta A or due to the moment at A is actually half of that MAB. Okay, so again, what I'm saying here is that the moment carried by that AB will induce half on the other end. Therefore, there will be an effect half on the other end. So that is a carryover moment. Okay, that is the carryover moment. So let's say again that in your member AC, since that is a fixed, okay, whatever is carried out from the excess in your joint A, whatever is taken by that member AC, there will be a 1/2, since that is a fixed end. There will be a 1/2 effect of that on the other end, which is your MCA later on. Okay, so that is if your member is fixed on the other end. Okay, how about if that is a simple support on the other end? Again, simple support, that could be a ruler or a hinge. So consider your member AD, that is a simple support on the other end. So whatever moment that will be carried on your AD is actually, that will not induce a carryover moment, since that is just a simple support. Okay, that is just a simple support. Why is it? Okay, why is it? Because again, okay, that is a simple support, so there should be no excess moment. So whatever is carried by that other end will not be helping, okay, this other end will not be helping, since again, that is not fixed support. That is not a fixed support. Unlike here, okay, if something will happen on the other end of that member, this will help. The other end will help, since that is connected as a fixed support. But in here, that is free to rotate. Therefore, it will not help. So again, for a carryover moment, if your other end is fixed, then that will be induced, or that will be receiving 1/2 of the moment received by its other end. If that is just a simple support, it's either ruler or hinge, then that will not receive any carryover moment. Okay, so that will be 0. Okay, so that is your carryover moment. Now, we need to discuss about this. This is important, structure with cantilever member. Since I think we did not discuss this one on the previous unit, in the previous module, okay? So what happens if there is a cantilever member? What happens if there is a cantilever member? Okay? So what happened there is to calculate the moment at the joint due to the cantilever member, which will serve as a fixed end moment. Your FEM is a fixed end moment to be considered on the joint. However, the cantilever member will not contribute to the stiffness of the joint. Therefore, it will not be considered in balancing the joint where it is connected. Okay, so what does that mean? Again, actually, if you will try to consider a joint D, this member DE, the cantilever member DE, will actually not help in resisting moment at joint D, since that is actually free to rotate. So as joint D rotates, that will just follow. Okay, that will just follow, since that is a cantilever. This is not supported at this other end. So, how is that? You can actually, in the analysis of consistent deformation, moment distribution, in this moment distribution method, we will try to cut the cantilever, and then whatever moment that is carried by that cantilever will still be there, but that will be later on applied only as the fixed end moment on the other side. But, again, since that member will not contribute to the stiffness, it means whatever is the excess moment at joint D, that will never ever receive any of that. So only, let's say that since in our case that is only AD, member AD and DE connected, but this is a cantilever, so whatever excess at joint D, that will only be carried by your member AD. Since again that is a cantilever, so it will not receive any of that. Okay? It will not help in balancing the excess at joint D. Okay, so again, that is what happened. So what happened there is you do not need to worry about your cantilever. All you need to do is cut that one. You can forget about that. All you need to do is calculate whatever moment, whatever type of loading here. Calculate the end moment at this one. Okay, so you do not need to be using here your fixed end moment formula, since actually just by taking moment at this cut portion, then whatever loads that you have here, since there are no unknown reaction in this side, you can summate all that moment, whatever that kind of loading here, then that is the fixed end moment on this side. So, okay, that will serve as additional fixed end moment on this joint D, but again, okay, I am trying to make this clear. This cantilever will never ever help in resisting a moment, the excess moment at joint D. Okay, so I will explain that one further later on. So these are now procedure of your analysis. All you need to do is follow this one. So first is determine the distribution factor. Again, why? Because we need to know how much of the excess moment on the joint will be received by each of the member connected. Okay. So, determine the distribution factor, that is again the stiffness of the member divided by the summation of the stiffness of all the member connected. But again, in cantilever, if there's a cantilever, do not add that one, since that will not help on the on carrying the moment. So, let's say again, at this joint D, there are a lot of members connected to that, then that is what you will summate. But forget about your member DE if that is the cantilever. Do not add that one in your stiffness, because that will not help in resisting the moment. Okay, so that's it. Find your what to call this one, distribution factor, and then once you have that, calculate now the loads or the moment on the joints. And what are these? These are actually the fixed end moment and the joint loads. Okay. So if we say joint loads, we are considering here a moment, since we are just actually analyzing moments. So if you have there again, if you have their member loads, if you have their loads on the member, okay, what you are going to do is transfer that one on the joints, since we are trying to balance the moments on the joints. So okay, so you have their loads that will be transferred on the joints. That is by means of your FEM. And of course, if you have there a moment on the joint, that will be a part of it. So, joint loads. And then, all we need to do now, once you have the moments on the joints, you need to analyze if there is an excess, of course. Okay, so we will try to summate the FEM, and if ever there are joint loads. Again, you need to satisfy that there are some joints on your structure that should not have an excess moment. For example, at this joint, there should be no moment at that. At this joint, there should be no moment at that, since that is not a fixed support. It's okay to have a moment at your B and C, since that is a fixed support, so that will receive the moment. Okay? So, now, if you have that existing moment on the joint, all you need to do is summate and balance, okay, this excess moment. Okay, we are only going to do that again, just like what I'm saying on the joints that are free to rotate. So again, these are the joints that are free to rotate. So summate the moments there, the excess, we need to balance that one. How to balance that one? Distribute that one on the connected members. If you have excess on the joints where that is supported fixed, then you do not need to balance. Why? Since that will be carried by the fixed support. Okay, so that's it. So we will be distributing whatever excess using your distribution factor. We will distribute the excess or the existing moment on the joints that are free to rotate. Now, again, as what I'm saying, there is no need for us to be balancing the moment on the fixed joints, since of course that will be carried by the fixed support. Okay. Now, second step is to carry over the moment. This is what I'm saying. Once you balance the existing moment on the joint, you will transfer that one on the ends of the members connected. Then again, there is what we call the carryover moment. So in this one, that will carry over 1/2 since that is a fixed support. Same thing with your AC, that will carry 1/2 of that to the other end. But in here, that will never carry over any here because that is not a fixed support. So it will not help. Okay? So that is your carryover moment. So again, that depends on the type. If in the other end that is fixed or in the other end that is just simple support. Now, once you are done with that, repeat the process again and again up to the time you will end up with equilibrium. If we say equilibrium, there should be no existing moment. There should be no existing moment on the joints, on all of the joints, except of course on the joint where that is supported fixed, okay, by a fixed support. In all of the joints that are free to rotate, you should end up equilibrium, or at least you will have their unbalanced moment, which is negligible. Okay, since this is actually what we call this one, iteration. So you will not expect that, especially if you are rounding values. Okay, since we will be repeating steps 3 and 4 again and again and again up to the time that you will end up equilibrium. But if not equilibrium, at least supposedly almost close to 0, or at least negligibly small, very, very small. Let's say that is 0.1 or 0.01. You can actually stop repeating the process 3 and 4. Okay, since again, that is the same as rounding values in your other methods, isn't it? That we will not end up with exact values since we are actually rounding values along the way. So it's okay. It's okay that we will not end up with exactly 0 as long as that is close to equilibrium. Okay. Then once you have it already in equilibrium or almost negligibly 0, then you can now calculate the end moments, since actually that is what we are after. Because once you have your end moments, just like in your slope deflection method, compute the end shears and then transfer this end shear and end moment on the joints, and then you can actually solve now the reaction, okay, of the structure. So how do you get that end moments? All you need to do is summate the fixed end moment, the joint loads, the balancing, and the carryover moment. Okay, we will have that one on the example. And then once you have that again, repeat the process just like in slope deflection. Compute the end shears for each member, determine the support reaction, and of course, you need to consider now, you can now check, once you have the reaction, you can now check the equilibrium of the total structure. Because, okay, that is the last way of checking if you really had correct solution. Maybe you will try to end up there with equilibrium and unbalanced, almost negligibly unbalanced moment. However, so you have something, you have a mistake in doing that one. So that will actually be seen if you will try now to calculate the equilibrium, or what we call this one, check the equilibrium of the total structure once you have now the supports of that. And once that is correct, your supports are correct, then you can now analyze any part of the beam or any part of the frame by drawing the shear and moment diagram if you need those. Okay, so again, as you can see, we will try to be repeating the process the process again and again. So this is step 3 and 4. Okay, once you have again an existing moment on the joint which are not supported fixed, or which is not
connected by a fixed support, you need to balance that one. Why? Because we need to make your structure stable. So any of the joints should be stable. So that should be in equilibrium. It's okay to have a moment on the joint which is again supported by a fixed support, but not on those that are free to rotate. So now, again, doing that, you will end up with a lot of solutions there. So it is suggested that you will present this one in tabulation form. We call this one actually the moment distribution table. Okay? Why? For us, of course, to have an organized solution, because again, what if? Okay, we call actually this one repeating your process 3 and 4. We call that one the iteration, or we call that one cycle. Once you will have the excess moment, balance that one. Okay, balance that one. That is one cycle, or one iteration. Then once, if you will try to, if there is still an unbalanced force, then you need to carry over that one. So another moment, another excess moment on the joint. So again, you need to balance that one up to the time again that you will end up with equilibrium, or again your unbalanced moment will at least be negligibly zero. Okay, so that is the procedure of analysis. You will better understand that if we will go on example.
Let's try to have this one. Okay, we will now try to go, again as I've said, moment distribution is for beams and frames. Okay, so again, just like your slope deflection, beams and frame without sidesway is almost the same. But once there is now a sidesway, that is now a different topic. Or there is just a slight difference with beams and frames without sidesway. So let's deal with your continuous beams. Okay, so in this unit, these are your desired learning outcome. Understand how moment is distributed at a joint of continuous beams by accomplishing what we call as the moment distribution table, or again, that is your solution, the moment distribution table. And then of course, our main goal here is to analyze and indeterminate continuous beams using your MDM, or moment distribution method. Okay, so let's try to have the same example as what we are having before on beams, so that we will always compare. Okay, so this is your example before. So what happened? Okay, so this is now what we call as the moment distribution table. Okay, so what will I do? First is, of course, identify the joints. So what are the joints? Okay, do not consider B and D as joints, since of course that is just where the load is created. So that is just still a member, still a single member. So your joints on continuous beams are A, C, and D. A, C, and E. I will write that down, A, C, and E. And then at joint A, that is only one end, only one member, so that is AC. And then at joint C, there are two connected members, so that is the member going to A, so that is CA. So just like in your SDE, or slope deflection method, we will try to follow the way of naming your end of the members. So AC, since that is at joint A, CA, since that is at joint C. And then this one, you have there the other end, which is CE. And we have there at joint E, your EC only. But you need to know, okay, you need to know if there are supports. Actually, there is a support here, but you do not need that one. You don't need to write that that is a ruler or fixed, since actually, even if this is a simply supported, if you are here on this joint, that will be considered as a fixed. Why? That is a continuous beam. So if ever there will be a moment, okay, let's say you have here this joint E, you will try to carry over a moment on that other end of CE. The moment that will be carried over will be carried by the entire beam here at the joint, since that is continuous. We will only be worrying on the end, which the member is terminated, just like this. That is terminated at A, but that is a fix. We need to know about that. That is terminated at E, but okay, that is ruler, so we need to know about that. It is ruler at C, but it's okay. You do not need to worry about that, since your frame is continuous. Okay, so that can carry a moment. Okay, you need to distinguish what are the joints. Okay, so joint, and then of course you need to know your members connected at that. So now, first step is to again, calculate your distribution factor, dF. But we cannot do that without your stiffness, bending stiffness, or your relative stiffness. In our case, your E is constant, isn't it? All the E, and actually the same, your I is also constant, but so therefore we will be using your relative. But if you want, you can still use your bending, which is together with E. Okay, so let's just use the K, not the K bar. So that is I over L. Again, I over L if the other end is fixed. Okay, you need to be careful with this. Okay, let me just get my okay, so let's have more complicated view. Let's say that's it. There are ruler. Okay, let's have 3 span. So your K here is I over L on this side. Why? Of course, that is fixed end. And this one, K there is still I over L. Why? Isn't it? This is a simple support. But again, as what I'm saying, even if that is supported only by a ruler or a pin, that is continuous. So it can carry a moment. So still, that will still be considered as a fixed end. Okay? So your K also here is I over L. Why? Because again, that is continuous here. However, in this side, that is 3/4 or only 75% of I over L, because that is now terminated in only a simple support. Okay? So, because you cannot see it there on a 2 span. So that is what happened. Now, let's go back here. Again, you do not need to be solving your stiffness at joint A since there are no other members connected to that. Okay, so, and actually that is a fixed support. So we do not need to be distributing whatever is the excess there because that will be carried by the fixed support. At joint E, the same thing. Even if there is an existing moment there, you cannot say that I will be distributing that one because that is only a single member connected. But let's say there is another member connected, and that's the time you need to solve your distribution factor. So you do not need to be solving your K, but if you want, you can do it. But again, that will be useless since we will not be using that one. Okay, now let's forget about that joint A and E. Worry about C. Okay, so get now the percentage that can be carried. If there is an excess at joint C, how much will be carried by AC and how much will be carried by CE. Okay, so again, this is your your K here. That is fixed there, so I over 10. That is terminated there. It is not continuous, and that is just a ruler, or even if that is just a pin, this is a simple support. So that is just 3/4 of its stiffness, or the stiffness of a fixed support. So that's it. That is okay. Our I, you can just say I there. You do not need to substitute since actually their I are the same. So I over 10. 3I over 40, but you can just forget about I since that is now the same. So, to get the distribution factor at CA, isn't it? Go back there, distribution factor is the stiffness of the member divided by the total stiffness. So, that is the distribution factor. So, the total there is, if you try to add 3 over okay, you can check that one, guys. 3 over 40, and this could be brought into 4 over 40. So 7 over 40. So this one is 4 over 40 divided by 7 over 40. That will be simplified as 4 over 7. And then doing the other way, the stiffness of this divided by the total stiffness, then that will be 3 over 7. So that is now our distribution factor. So that means if there is an excess moment at C, 4 over 7% of that will be going to CA and 3 over 7 will be going to CE. Okay? So again, that is the first step, distribution factor. Now, calculate now the moments at each of the joint. So, what will be the moment to be carried here? Forget first about the reactions. That is just a reaction. That is not yet present, okay? Or that is imaginary. So, at joint A, is there a moment load? No moment load. But there will be a moment to be carried because there is a member load. So, again, member loads will be converted into fixed end moments. So, try to calculate the fixed end moment of that. It will be going there as negative, isn't it? PL over 8 again. Before, we have that PL over 8. This is counterclockwise, so negative. And in here, PL over 8 clockwise, so 150, positive. The same here because they are identical, negative, positive. Now, that is your FEM. What else? You need to consider if there is a joint load, moment, or moment joint load, but there is no moment load at the joints. So, none. I do not need to be writing there any. Or if you want, you can write there 0 so that you will not be confused. So, now, okay, let's try to see the equilibrium state of all the joints. In your joint A, there is if I will summate the fixed end moment and the joint load, since that will be the moment at the joint, is a negative 150 all in all. However, I do not need to be distributing that one. I do not need to be transferring that one on the member because, again, this is a fixed support. So that whatever is moment there, that will be carried by the fixed support. So, again, we do not need to be balancing that one. Again, second step, isn't it, is to balance. Second is to calculate. We already done that one. We already did that one. Third is to balance now. However, again, there is no need for us to balance since that is a fix, so that will be carrying. In joint C, if I will try to summate all of that, the joint load and the FEM, 150, negative 150, that is actually 0. So this is originally in equilibrium. Joint C is originally equilibrium. Okay, so there is nothing to be balanced. Okay, so the balance of that is 0. In here, I put their dash. It means you do not need to be balancing since that is a fix. But in here, if ever there is an excess, you need to balance that. Okay? And then, of course, your joint E, summate your FEM, positive 150, and joint load, which is 0. That is a positive 150. So, I need to balance that. However, I do not have other members to carry that one, only your EC. So, that will just be balancing by negative 150. Again, as I'm saying, we are trying to balance. So, in balancing, that should be opposite sign. Okay, it will be distributed and all the members connected and at the same time opposite sign. So, there is an existing, this is positive, so clockwise. So, I will counter that one by the member by a negative. So, negative 150. Okay, we are done with the first cycle. However, let's try to look at this. We balance that. So, it means I just transferred a moment on your member EC. Okay, in here, no problem. There is nothing to be transferred. But in your joint E, I transferred a negative moment at member EC. So, what happened? That is not equilibrium. So, what will I do? I will apply the carry over. Carry over. So, this one, carry over. Okay, your EC will try to transfer some of that moment to your CE on the other end. So again, that is considered to be fixed since that is continuous, isn't it? So, what is the carryover? 1/2. So, 1/2 of that, 1/2 of negative 150 will go there to your CE. And then, there are no other existing moment that we will be carrying over. So, that is the only force or moment that we will be carrying over. Now, again, look at this. There is no moment here, but there is a moment at joint C. Because of that carried over, there is now a moment at joint C. So that is not equilibrium. Here, there is no transferred moment at joint E. So, there's no problem about that. So, I need to balance that. So, okay, due to the moment CE, which is negative 75, I need to distribute that. That is now a moment at joint C. So I need to distribute that at B at CA, and again distribute that one at your CE. Because what is carried over will be on the total joint. Okay? So summate this one, the total on the joints. Okay? Distribute that one by multiplying it with this distribution factor. Okay? Balance that one. But again, opposite sign. This is a negative 75. So make it positive and then multiply 4 over 7. That will be 300 over 7. Okay? That will be 300 over 7. Again, positive 75, make it positive since we are balancing. Multiplied by 3 over 7 is 225 over 7. Now, there is again a balanced fact, or there is an existing moment because of the balancing. I just transferred the moment on the members CA and CE. So what happened is I will now carry over. There will now be an effect on the other end since I transferred that on the member. However, this moment CE will not be transferring any to your other side CE because actually that is a simple support, isn't it? Go back again there. Carry over moment. Carry over. What's that? Carry over. Carry over. If that is a simple support, there should be no carried over moment. And if that is what we call this one, a fixed, that is just one half to be carried over. Okay, so that's it. Since the other end of that CE is simple support, so nothing will be carried there. So still that is 0. Okay? In this one, we'll be carrying over, since that's a fixed, on the other side, one half of that. So 150 over 7. Now, again, this one 0, so nothing to balance, that is still 0. This one, balance that one, but we do not need to balance since that is a fixed. Okay, so we are good. Look now on this row. There is nothing to be balanced since that is fixed. There is nothing new. And of course, because that is 0, the carried over is 0, there is nothing new. So we are done. Okay? This is the time that you will have an exact answer. You will really end up with nothing or 0. But there are some cases wherein this process will continue again and again and again, only that these values will just become smaller and smaller and smaller and smaller. So if that is the case, maybe if you will now end up with 0.1 or 0.01, you can stop, okay, the cycle. Again, this is the cycle. Moment on the load. This is your original, isn't it? Originally, you have the moments on the joint, moments on the joint. Transfer that on the member in your balancing. That is one cycle. You have the existing moment, distribute, one cycle. And then if that is now distributed, there should be an effect on the other end. So that is your carryover. And because of the carryover, there will now be a moment on the joints. And then again, balance that one. So another cycle. So look at this. The first cycle is the load, balance, one cycle. Load, which is the carryover, that is a load. Balance, another cycle. Load, balance, load, balance. So that is the cycle. Load, balance, load, balance, load, balance. Okay, so that is the iteration we are talking about. Up to the time that everything will be balanced. So repeat the process of carryover, balance, up to the time it will be totally balanced. Or at least, if that is not exactly balanced or 0, at least the unbalance will be at least 0.1 or 0.01. Okay? So now, again, we are not done. We are not done yet. Because those are only carried over and balancing. What is next is that solve now your end moments. What are the end moments, so that we will transfer that on joint and then solve for the reactions. So all you do is summate your if-EM, joint load, balancing, and the carryover moment on the joints itself. So if you want to get the end moment AC, all you need to do is summate that row, and then that will be the fixed the end moment at AC. Okay, that's it. And then if you need the end moment at CA, just summate that column. Load, balance, balance, and so on and so forth. Summate that one. And same thing happens in all of that. And again, this is again just like before on the slope deflection. If that is a joint which is actually not supported by a fixed support, the summation of moments there of the end moments should be 0, which is in our case correct. That is how you will check. That one, that should be originally 0 since there is no fixed support or there is no moment here. So nothing will be counteracting that one. So that should be 0. So we are correct. Another way of checking. However, in your A, that is only a negative 900/7. You do not have something to counteract that one because that will be carried by the fixed support. So, these are your fixed end moments. Negative 900/7, counterclockwise. Again, that is our assumption for the fixed end moment. Clockwise positive. So, positive is clockwise. Negative is counterclockwise. 0, so nothing. Now, the same thing happens. Get your shear, end shears. And then, of course, once you have your end shear, transfer that one on the supports. Now solve the reactions. And you will end up with exactly what we have using the consistent deformation, using the slope deflection. If you try to compare our answer, that is the same. Okay? So that's it. Continuous beams using your moment distribution. So I will just try to again recap the steps. First, you need to know if there are more than one members connected, get or solve the distribution factor. But in here there is only one, so I do not need to do that. The same thing with this. And then in this C, okay, now get your stiffness, get the percentage or the distribution factor. Again, stiffness all over summation of stiffness of all the members on the joints. And then, now I will start in knowing what is the original moment on the joint. So that is again, if there are loads on the member, there should be fixed end moments. If there are joint load, which are moments. Okay, we are only considering a joint load which are moments since we are just distributing moments here. However, in our case, there are no moments, so 0. Nothing. Now, what you are going to do next is balance that one. Okay? You do not need to balance since that is a fix. Okay? We will be balancing, but that is originally equilibrium, 0. So, nothing to be balanced. But in here, there is a fixed end moment which needs to be balanced because that is not a fixed support. So, I need to balance that. So, again, balancing should be opposite sign. So 150, negative 150. There is no other connected member for us to distribute. So only exactly the same negative 150. Now, look at this column of balancing. It's okay, nothing. But there is now on this joint E. So we cannot stop as long as it will be totally balanced in all of the joints. That's why we are using a tabulation. Okay, so this one, there is a balancing there which is transferred on the member, so that will inflict and carry over on the other end. That is continuous, so that is considered to be fixed. 1/2 will go on this side. And then, of course, there is nothing for us to carry over, only that. But since because of that carried over, that will make your C unstable or not equilibrium. So I need to balance that one again. Summate all of that. So happen that this is 0. Summate this. And then multiply, distribute, balance again, so opposite side. Then because of that balancing, that will make this again unstable because there is a value here. So I need to carry over again. 1/2 of that will go there because that is a fix, and nothing will go there because that is a simple support. That is not a continuous. So that is just a simple support. So nothing will go there. So balance this, which is still 0. But this one, if I will balance that, you do not need since that is a fixed support, so it will receive that unbalanced moment. Now we are done. Look at this balancing. Nothing already. That is already balanced. So summate, that is the end moment at AC, summate, end moment at CA, summate, end moment at CE, summate, that should be 0 since there should be no end moment since that is simple support. Okay, again, so the same thing happens again. So that is continuous beams. These are the important concepts. So in MDM, all loads are transferred at the joints of the structure. So that is what I'm saying. If there's a load on the member, convert that one as a fixed end moment. And then to satisfy that all joints shall be in equilibrium, okay, the excess and balance moment at a joint is distributed on the joints adjacent to it. Okay, how is that? If there is an existing moment at this joint, that will be transferred on the member, and the member will carry over on the other joint. So that's it. We are still focusing on the joints. The member will just serve as a relay or a bridge for us to carry over the other moments, the moments on the other joints. But again, there should be no carrying over if the other end is terminated and it is just a simply supported. If that is a fixed, then what will go there is 1/2 will be carried over. Okay, consider a sign convention. Okay, so this is the same in your SDE. If your sign convention in your FEM, clockwise positive, you should follow that all throughout. So that's it. Okay, and as what I've said a while ago, continuous beams is almost the same as frames without sidesway, just like in your SDE or slope deflection method. So let's try to continue it now on this video. Okay, so frames without sidesway. So again, the same learning outcomes. So we will just try to deal now with frames without sidesway, of course. Okay, so let's try to have this. This is actually a new example. We did not have this before. So I consider this because at least there are all of the cases is here. All the cases are here. Okay, so again, I consider this example since the cases will be actually encountered here. So this is your frame. You have this A, B, C, D, E joints, and these are your loading, the UDL from B to E, and the force at the middle of your member AB. So there is no force or there is no load in your CD, so that there should be no fixed end moment there. So again, the same, stick to the process. Try to pinpoint the joints. So joint A, joint B, joint D, joint E, joint C. Okay, so it's up to you. By the way, there is no such as standard form of the table. It's up to you to create your table. So you can actually interchange where you will put the joints. But of course, it is always better for you to arrange into a manner that you can just actually look at this. I will arrange it this way so that AB, this one member AB, if I have something here to be carrying over, that will just be going here. And that next there is D, so that is BD, since we have their member BD. If I have something to carry over, that will just go there. And then, of course, that is a little bit complicated at joint D, since there are three. Since there are three members connected to that. So it's okay with the first one, that is your other end. The other end is E, but I cannot, of course, put there the other end C. So I need to separate that. So again, carry over B, this will be carrying over with each other. DE, I will write E there so that will be carrying over with each other. So the only problem is for me to carry over your DC here. So I need to write there your CD, separate here, so that this is now the carrying over on this column, carrying over on this side, or vice versa. Okay, so it's up to you. Design your table for you to have convenience on solution. So first is your stiffness. So again, no need for A to get your distribution, since that is just a single member. The same thing with E. Single member, single member, single member. So A, C, and E, you do not need to be solving the distribution factor. Only at B and D, since these are more than one member. So first is member B. Member B, so BA and BD. However, your lengths are different. This is 10 and 10, so the length is 20 of the columns. But these are 30, so the lengths of the beams are 30. So, and at the same time, your I are different, so you need to consider that one. So, okay. At member AB, at joint B, member AB is I over L. So I over 20. I over 20. You do not need to be multiplying it by 3/4 since that is a fix. The other end is fixed, so we are good. At BD, okay, that is still considered to be fixed since that is a continuous at this point. It is not terminated. So we do not need to multiply. So that is I over L, but the I of this is twice. So 2I over 30. 2I over 30 will be simplified as 1 over 15. So that is our I, the stiffness on BA and BD. So get the distribution factor. Add this one. This divided by the summation is 3 over 7. This divided by the summation is 4 over 7. You can check that one. And then on joint D, okay, so D going to B, D going to C, D going to E. So for this, that is the same as stiffness here since that is continuous there. So 2 over 30, 1 over 15. For DC, that is fixed there, so it's still I over L. I over L, which is 20, so 1 over 20. And for your DE, okay, why is it there is a 3/4? Because this is terminated and that is just a simple support. So 3/4 or 75% of the I over L, but the I of that is 2I over 30, so that is 3/4 of I over 15. Okay, we're good. Get now this distribution factor, summate, divide it by the total. So I divided by this divided by total is 2 over 5. This divided by the total is 3 over 10. This is actually 0.4, 0.3, and 0.3. This, if you will multiply 3 over 40, I mean this is 60, isn't it? Yes. 3 over 60 can be reduced to 1 over 20. So the same, 3 over 10. Okay, again, just the distribution factor. Now, fixed end moments. There is a fixed end moment at AB that is PL over 8. Negative at A because, okay, it will be countering that way, so counterclockwise. So negative at AB and positive at BA, which is PL over 8. Our PL over 8 there is 100. Negative at AB and positive at BA. Then fixed end moment, the fixed end moment here at BD, WL squared over 8. So that is again negative at B, positive at D. Negative 150, this is WL squared over 8 again, you can check that one. Negative at B, positive at D. What else? This one, DE. So positive again, positive at D, negative at E. Positive, I mean negative at D. Sorry about that. Negative at D, positive at E. Negative, positive. And in your, what's that? CD, there is no load, so there is no fixed end moment. So DC and CD are 0. And are there joint moment load? There is no moment loads on the joints, so we are good with that joint load. So 0. Now, again, let's start. Okay, you need to know what are the types of support. This is fixed. AC is fixed, E is pin. AC is fixed, E is pin. So you need to write there if that is a pin or fixed so that you will know. Again, the difference of this will matter on the carryover and on the balancing. There is a moment at A to be balanced. However, that is a fixed, so that will receive. There is no balancing. At joint B, if I will summate, you will end up, okay, if I will summate a negative 150, distribute that one, so it will become positive since we are trying to balance that one. 50 times 3 over 7 will be 150 over 7. 50 times 4 over 7 will be 200 over 7. Okay? And in here, summate, it is actually 0, so there is nothing for us to be balancing. Okay? 0, nothing. Nothing for us to balance. Okay, at joint E, that is pin. So yes, we need to balance that. 150, so negative 150. Nothing to be distributed. At C, nothing, so nothing. And that is fixed. So you do not need to balance. Okay, so we have now a values on your balancing, so you need to continue. Carry over. BA will go AB. Fixed, so 1/2. This will go there. Continuous, so considered fixed at D, so 1/2. Okay, what else? This one. E. will be carrying over there 1/2, since again that is the pin but the other end is continuous, isn't it? This is pin but the other end is continuous, so we can transfer half of that. Okay, so that is the only balance that we need to transfer. So carry over, balance that one again. You do not need to balance this since that is fixed. You did not have any carry over from DC because there is actually no load at CD. So that's okay. But that is the total joint, so summate everything that is in the joint. Summate that one multiplied by 2/5. This will be, okay, you will end up with a negative summation, so balanced by a positive. Multiply this one, multiply, and so on and so forth. And then that's it. That is the only thing that we will be balancing, isn't it? That is the only joint that we need to balance. Nothing. Here, you do not need since that is fixed. Now carry over the balance. Okay, so this will go half there since that is continuous at B. This will go half on the C because that is fixed. But this one, DE, will go 0 on ED because again that is a pin and E is terminated. So that should not be carrying any carry over. So that should be 0. So again, there is still a carry over, so we will not stop. So this is now, there is no existing moment at joint B. So balance that one again. Positive, so that will now be balanced by negative. Multiply there, this one. Multiply there, this one. And what else? This one, balancing that 0 is still 0. This one, do you need to balance that? No, because that is fixed. That will be carried by support. So we're good. But if you try to look at this row, there is unbalanced force. Okay, you might be thinking of stopping, but if you try to calculate this, 255 divided by 49 is a big number. Almost 4 point something, almost 5. So that is a big moment. So we should still continue. So again, carry over half of that. Carry over half of that. Then there is nothing more to be carried over since this is of course 0. And then once you have that, you do not need to balance since that is fixed. This one we need to balance. So summate all of that, but this is the only moment at joint D. Negative, so balancing is positive. Multiply to 2/5, you will have that. Multiply to 310, you will have. Multiply to that, you will have this. This balancing, look at that. This 68 over 49 is still bigger than 1. So we cannot stop. We need to continue. Another cycle. Again, another cycle. So carry over half. Carry over half of that on the this is DC, so that will go CD. And this one, carry over, but that is a pin, so that should not be carrying any. So 0. So balance that is still 0. You do not need to balance since that is fixed. What else? In here, balance this one. Balance this again positive, so you will have a negative balance. So multiply there, you will have. Multiply, you will have. Okay. If you try to look at this, this is less than 1, but maybe that is I think 0.1 something. So I think it is better if we will continue further. Okay, so no. 102 divided by 300 is almost 1/2, or that is almost 0.5. So that is still big. So maybe I will continue. Okay, so carry over. Carry over. So nothing else to be carried. That is 0. And then balance, no need since that is fixed. Balance. So 2/5 of that, and so on and so forth. Okay, so actually these are fractions. But for us to see if that is almost 0, it is better for us to transform in decimal. And if I were to transform that in decimal, the values here, this is a negative, so your balance is positive. Check that one in decimal, that is 0.08 something. Actually, this is rounded. These are all rounded. But that is 0.08, 0.06, 0.06. So almost 0. As what I've said, if that is 0.1, you can already stop. Okay? Comparing that with the original moments. The original moments are big, 150, 100, compared to 0.8 or 0.1. That is small. Negligibly small. So we can stop. If you want, you can further continue, but there will just be a slight difference on the answer only on the decimal part. Okay? So again, we call this one the iteration. So how many cycle? from the load to balance, 1, com balance, 2, com balance, 3, com balance, 4, com balance, 5, com balance, 6. So we did 6 cycles. Okay, we did 6 cycles. Comparing to your beam a while ago, only I think 3 or 2 cycles there, because of course there are less members. In here there are more members, and there are more what we call this one, joints. So the more the joints, unless of course it will be balanced right away. Okay, but again, you do not need to make that exactly 0, because again you need to have a lot of cycles to do that. Because as you can see, this one, big fraction, small fraction, up to the time it will just become smaller and smaller and smaller. So that will take time to be 0. So now get your fixed end moment, summate from the load down. You will have a negative 92.04. Load going down is positive 155.93. Load going down is negative 155.93. Which is supposedly correct, because that should be 0. Since that is a joint B, there are no support there. At joint A, it's okay, since that is fixed. So that will carry that one. At D, summate, that's it. Summate, this is, summate, this one. Okay, again, just like here, you need to summate, these are only 2, so you can see right away. But in here, if you will try to summate, that is negative 0.01. Again, why is it 0.01? Because of, again, rounding here. But it's okay. That is just small. Very, very small. 0.01. So it's okay. Okay? Again, because we did not end up exactly 0, so you will expect there a slight only. Negative 0.01 or at least 0.01. So we are good. We are still good at joint D. And then E, summate, of course, 0. Why is it 0? Because E is not a fixed support. So that should be 0. So we're good. And then summate at C, that is 9.63, because that is fixed. So it will be carried. Okay. All you need to do is transfer. Okay, so again, it looks complicated, but this is as simple as writing your end moments, solve your shear. Okay, so you can do this one, guys. This one, okay, solve the shear. Okay, you can do that one since we had a lot of this. And if you will try to solve that shear, summate, that should be equal to this. So we're good. Moment and then shear. Okay, summate your shear, that should be equal to 2 times 30, which is 60. We are good. Solve your end shears. Summate, that should be 60 again. 20, 36, 23. It's good. It is 60. Okay, and then in here, summate, there is no member load, so the end shear will just be opposite direction, but the same value. So we're good. Now all you need to do is transfer the end shear and moments on the joint. Okay, we already checked that the moments are good. Okay, so you do not need to worry on the summation of moments on the joint, because in here, no problem. In here, no problem. We already checked that one, and you cannot proceed if these are not 0. Okay, you cannot proceed if any, or let's say, if even 1 is not balanced, then you cannot proceed. You need to continue that one, or that means something's wrong with your solution. Okay, so that is how we will check. It's okay. There are values here since these are fixed support. So this shear will go down. That will become the axial of this member here, which is 27. This shear here will go there, axial. Will go there, but that is not the only shear that will be going. We need to have the shear also of this. So 36 will go down, 32 will go down. If I will summate that, that will be equal to 69.21. That is the axial of your member CD. And in here, transfer that there, that is actually the reaction vertically, since there is nothing for us to be cancelling that one. So VED is 23.14, that is now your reaction EB. Your axial, which is actually, look at this. The shear here will go as the axial, so 21.19, and it will be transferred here. And again, the shear will go on top, so that we will go there, okay. This axial will transfer on this, from left it will go right, and you need to have that shear on your D, it will be transferred there, from left again it will go right. So therefore, the total action here is the summation of the axial dB and the shear of DC. So summate that one, that is your FDE, which is your axial in your member DE. So 32, wait. I think, wait. No, not this one. This is what I'm saying. So FDB, that is the axial. 21.19 plus, isn't it? That is plus, since the same direction as this. 1.45 will be 22.64. That is the axial. It will be going there, and that will now be going as the reaction EH. Okay, and now go there to this joint. This is coming from the summation of shear here, isn't it? So 69.21, that will go down, it will go up, it will go down, it will go up as a reaction, which is 69.21. Okay, why is that? Okay, let's just, why is it the case? Okay, let's just adjust so that it is nice for us to recognize this. Yeah. Okay, so again, that 69 will be your CD, which is 69.21 kips. Okay, that shear CD is going to the right, it will go to the left, so the reaction is going to the right, 1.45. Okay, the moment is clockwise here, 9.63, it will go counter, it will go clockwise again, 9.63, keeps fit. Okay, so we're good with the reaction at C. In here, transfer everything. Okay, so going to the left will go to the right, so your reaction is to the left, 18.81. Going up, so that will go down, and so your reaction is going up, 27.65, 27.65. And then moment is counterclockwise, it will go clockwise, it will be going counter again, 92.04, 92.04. Okay, so we are now having your reactions. I do not have space here to write the outline, so again, we can actually use this one. So these are now the reaction. We are done. All you need to do is check. Of course, check the equilibrium of all of the entire structure. So look at this. Summation horizontal. So the only horizontal is 40. Horizontal load. So this is the horizontal, that is the horizontal, this is horizontal. I will sum it. Look at this. To the left, 18.81. To the left, 22.64. That is more than 40. But since that is on the opposite side, which will be, okay, you can check that one. That is, I'm pretty sure, and I'm really sure that is exactly 40. So 18.81 plus 26.64 minus this is equal to 40. Now vertical. What are the total vertical loads? This is 30 times 2 is 60, and that is 60, so supposedly 120. So 27.65, 69.21, 23.14. If you will add that one, I am pretty sure that is total 120. And then how to check the moments? You can take moment here, you can take moment any point that should be satisfied, or at least if you have their 0.01 or negative 0.01, it's okay because of the rounded values. So that's it. It is almost just like a beam, isn't it? Nothing happened. No difference with the beam. We just followed your procedure. Again, what's that? Get your distribution factor. If there are more than one member connected, now start by getting the moment load on the joint, which is your fixed end moment, and add if there is a joint load moment. Okay, once you have that, try to now summate. If there is an existing moment, then balance that one, distribute that one using your distribution factor. But do not forget again in balancing opposite side. Okay, there is no need for us to balance on the fixed joints. Okay, on the fixed joints, that should not just be joints, fixed support. Okay, or let's say fixed joint because of the support. And then of course carry over. If there is now, if your balance is transferred on the beam or on the member, you need to have a carryover on the other end, and that will only happen if it is not terminated with simple support. Because if that is terminated with simple support, there should be no carryover. Repeat the process again and again up to the time you will end up with equilibrium, or at least almost zero existing moment. Then get your end moment, submit the column of your table, and then proceed and so on and so forth. So again, this is how we will solve this one using your distribution table so that it will be organized and arranged. You cannot do it as solution here, solution there, and so on and so forth, because that will just be a lot for us to follow, and that will be messy. Okay, so that's it. Moment distribution method on continuous beams and frames without sidesway. The frames with sidesway will be another video. Okay, so if you have question, you can comment below the video, or you can ask that one on the next live meeting. So thank you very much for watching.